As of May 2nd, 2026, NOAA's Space Weather Prediction Center is registering an active R1 radio blackout condition on the sunlit side of Earth, the consequence of a sun that has not been quiet for a single full week since late April, driven by two sunspot regions, AR4420 and AR4425, both carrying the most magnetically dangerous classification a solar physicist can assign, beta gamma delta, the configuration that means tangled magnetic fields under extreme pressure, holding energy the way a dam holds water, and capable at any moment of releasing it all at once. In the 6 days leading into today, May 3rd, 2026, the sun fired 23 flares in a single 24-hour window. 3 of them M-class events, all originating from AR4420, the most active of the two regions, and NOAA's Space Weather Prediction Center formally issued a 70% probability of further R1 to R2 radio blackouts, continuing through the coming days. That number, 70%, is not a figure chosen for dramatic effect. It is the measured probability that high-frequency radio communication, the band between 3 and 30 megahertz that aviation, maritime operations, military coordination, and emergency services all depend upon across the sunlit hemisphere of Earth, will be degraded or silenced entirely. The sun is accumulating, and what accumulates eventually releases. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources. NOAA's Space Weather Prediction Center at SpaceWeather, Gov, NASA's Solar Dynamics Observatory, the European-based Space Weather Live Monitoring Network, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. When the sources are listed, the data is public. The responsibility to check belongs to all of us. But that is not even the complete picture. What the monitoring data from the past week reveals is not simply an active sun producing moderate flares and occasional radio interference. What it reveals is a solar system in a specific and historically documented phase of behavior, a phase in which the sun, even while declining from its 2024 peak of solar cycle 25, retains the capacity to produce the kind of events that have, on documented occasions with confirmed dates and confirmed consequences, brought entire power grids to their knees, sent satellites tumbling uncontrolled through low Earth orbit, and left millions of people in the cold and dark while emergency crews scrambled to understand what had happened. The radio blackout risk registered today is not the story. It is the symptom. The story is older, and it is encoded in the geological record, in the ice cores of Antarctica and Greenland, and in the circuit boards of every satellite currently orbiting this planet, a story about what the sun is capable of when the conditions align, and about how spectacularly unprepared the modern world remains, even now, even with its fleet of monitoring satellites and its real-time alert systems. For the day, those conditions come together again. To understand what the instruments are measuring today, it is necessary to understand the architecture of what a solar flare actually does at the level of physics, not in general terms, but precisely, because precision is what allows the human mind to feel the actual weight of what is happening. The sun's surface, what scientists call the photosphere, is not a uniform burning sheet. It is a churning, turbulent plasma ocean punctuated by regions of intense magnetic activity. These regions, visible to the naked eye with appropriate filtering as dark patches, sunspots, are areas where the solar magnetic field has broken through the surface with such force that it suppresses the convection of hot plasma, making those spots appear darker than their surroundings. They are not cold, they are merely cooler than the infernally hot surrounding surface. A large sunspot is still hotter than any fire that has ever burned on Earth. But within the structure of a sunspot group, particularly one with the beta gamma delta magnetic classification assigned to AR4420 right now, the magnetic field lines from regions of opposing polarity have become so tangled and stressed that they cannot maintain their configuration indefinitely. When the field lines snap and reconnect, a process taking minutes, sometimes seconds, the energy released is equivalent, in the largest events, to billions of hydrogen bombs detonating simultaneously. That energy propagates outward in 2 distinct forms, and this distinction is everything. The first form is electromagnetic radiation, X-rays and extreme ultraviolet light, traveling at the speed of light, arriving at Earth in 8 minutes and 20 seconds. This is the radiation that strikes the D layer of the ionosphere on the sunlit side of Earth and ionizes it. The ionosphere, under normal conditions, is what makes long-distance high-frequency radio communication possible at all. Radio waves in the 3 to 30 megahertz band bounce off the upper layers of the ionosphere the way sound waves bounce off the ceiling of a large hall. The ceiling directs the sound outward, extending its reach far beyond what the direct line from the speaker can achieve. When a strong enough flare strikes, the D layer, the lowest, densest part of the ionosphere, becomes saturated with free electrons produced by that intense radiation. In that saturated state, the radio waves do not bounce. They are absorbed. The ceiling disappears. The signal drops to nothing. This is a radio blackout, and it happens at the speed of light, meaning there is no warning interval between the flare and the communication failure. The two are simultaneous. What NOAA classifies as an R1 event, the current condition on May 2nd and 3, 2026, produces weak to minor degradation across the sunlit hemisphere. An R2 event, which NOAA assigns a 70% probability of occurring in the near term from active regions, AR4420 and AR4425, produces limited but significant blackouts lasting tens of minutes. An R3 event, which carries a 25% probability under the current conditions documented in NOAA's official alerts, produces a wide area blackout of HF radio communication for approximately 1 hour. And at R5, the maximum level on the NOAA scale, complete HF radio blackout on the entire sunlit side of Earth occurs, with no recovery for hours. Aviation over transoceanic routes loses its primary backup communication system. Maritime vessels operating beyond the reach of modern satellite uplinks go silent. Emergency coordination between national agencies degrades. The second form of energy from a major flare is the coronal mass ejection, the CME. This is plasma, magnetized solar material, billions of tons of charged particles, traveling not at the speed of light, but at speeds between 400 and 3,000 kilometers per second, arriving at Earth not in 8 minutes, but in 1 to 3 days. And this is where satellites enter the story in a way that is not theoretical, but documented, confirmed, and sobering. What is critical to understand about the current situation on May 3rd, 2026, is that the NOAA Space Weather Prediction Center's official alert records confirm that following the M6. Zero flare produced by AR4420 on April 26, 2026 at 22 to 57 UTC, an event accompanied by a Type 2 radio sweep estimated at 834 kilometers per second. The question of whether a coronal mass ejection accompanied that eruption remained under investigation by NOAA forecasters. The M6 flare produced at 22:57 UTC on April 26, confirmed at R2 moderate blackout level in NOAA's official summary, was accompanied by a 10-centimeter radio burst of 260 solar flux units. That radio burst matters because a 10-centimeter burst at that level is defined by NOAA as indicative of significant radio noise that can cause interference for sensitive receivers, including radar, GPS, and satellite communications. Now consider the context. The 7-centimeter radio flux measured by NOAA on May 1st, 2026, stands at 143 solar flux units, a figure that reflects a sun actively producing energy across the full electromagnetic spectrum. The sun, on May 3rd, 2026, is not quiet. The sun is loaded. Here's where this account becomes genuinely significant. The people living directly beneath the maximum impact zone of an R3 or greater radio blackout are not abstract coordinates on a map. They are the pilots of transoceanic flights over the Pacific, where high-frequency radio remains the primary backup communication system when satellite uplink fails. They are the fishing crews operating 300 kilometers off the Atlantic coast, beyond cellular range, whose vessels carry HF radio as their lifeline to shore coordination and weather updates. They are the air traffic controllers in northern Alaska, in Iceland, in northern Canada, regions where satellite coverage has gaps and where high-latitude radio communication absorbs more ionospheric interference even under normal solar conditions. Canada, whose population lives at higher latitudes than almost any other major nation, is not simply geographically exposed to space weather. It sits beneath the auroral oval, the ring-shaped region centered on the geomagnetic pole where solar particles concentrate, where radio absorption is deepest and where the effects of even a moderate solar radiation storm are felt first and most severely. Consider the city of Yellowknife in Canada's Northwest Territories, a population of approximately 20,000 people, connected to the south by highway, by satellite communication, and by HF radio emergency coordination. That city, and the dozens of communities like it across the Canadian North, along the Alaskan coast, across the Scandinavian countries of Norway and Sweden and Finland, where hundreds of thousands of people live their daily lives within the auroral oval, these are the communities for whom the 70% probability NOAA has registered is not an abstraction. It is the weather report. The second form of community that must be named is the one operating closest to the threat that most people never consider: the satellite operators. There are, as of 2026, more satellites in orbit above Earth than at any previous point in human history. The communications infrastructure of the modern world, GPS navigation, internet backbone services, weather monitoring, military reconnaissance, television broadcasting, financial transaction routing, is carried largely on orbit, and orbit is not safe when the sun erupts. The mechanisms of satellite damage during a solar storm operate on multiple pathways simultaneously. The first is direct radiation impact, high-energy protons and electrons from a solar radiation storm penetrating satellite shielding and depositing charge in sensitive electronics, causing what engineers call single-event upsets, bit flips in memory systems, logic errors in control circuits. NASA's TDRS-1 communication satellite recorded more than 250 anomalies of this kind during a single geomagnetic storm event, an event the scientific record dates precisely to March 13, 1989. That number is documented. That satellite was a functioning operational spacecraft, 250 anomalies in a single event. The second pathway is atmospheric drag. The thermosphere, the outermost layer of Earth's atmosphere where satellites in low orbit travel, expands significantly during geomagnetic storms as the solar energy heats it. The expanded atmosphere creates increased drag on low orbit satellites, decelerating them, altering their trajectories, requiring emergency orbital adjustments, or risking re-entry. This is not speculation. In February 2022, a geomagnetic storm was responsible for the loss of up to 40 of the newly deployed Starlink satellites, which were dragged out of orbit before they could raise themselves to operational altitude. And the third pathway is magnetospheric compression. The boundary of Earth's magnetic field, normally sitting approximately 65,000 kilometers above the surface on the sunlit side, can be compressed inward during a severe geomagnetic storm to the altitude of geosynchronous orbit, approximately 36,000 kilometers, exposing communications satellites to direct solar particle bombardment that their shielding was not designed to withstand. This is not a hypothesis. This is documented in the geological record, in satellite telemetry archives, and in the confirmed event history maintained by NOAA, NASA, and the European Space Agency. And it has happened before at a scale that makes the current 70% R1 to R2 probability look, in hindsight, like the first tremor before the main event. On March 13, 1989, the sun did something that the modern world, even in its Cold War state of technological sophistication, was entirely unprepared for. Two separate coronal mass ejections had left the solar surface on March 10th and March 12th, the first produced by an X4, 5-class flare, the second by an M7, 3-class eruption. The first ejection traveled ahead through interplanetary space and cleared a path, compressing and heating the solar wind ahead of it, making the plasma environment through which the second ejection traveled less resistant and more conductive of its energy. The second ejection struck Earth's magnetic field on the evening of March 12, 1989, and what followed became one of the most consequential documented space weather events in the technological age. The geomagnetic storm that developed peaked at a KP index of 9, the maximum value on the 9-point geomagnetic disturbance scale. Just after 2:44 in the morning on March 13th, geomagnetically induced currents flowing through the rock of the Canadian Shield, the ancient Precambrian bedrock underlying Quebec, which, because of its extraordinary electrical resistance, forced current to flow not through the ground, but through the high-voltage transmission lines of Hydro-Quebec, overwhelmed those transmission lines in under 90 seconds. In less time than it takes to walk from one end of a city block to the other, the entire power grid of the province of Quebec failed. 6 million people woke up in the dark and the cold without understanding why. The blackout lasted 9 hours. Schools and businesses closed. The Montreal Metro shut down during the morning rush hour. Dorval Airport closed. At a General Motors plant in Montreal, the production loss was calculated at $6.6 million for 8 hours of halted assembly. Across the United States, more than 200 power grid problems erupted within minutes of the storm's onset, none producing a blackout, but all registering the signature of a system pressed to its limits simultaneously from coast to coast. And in orbit, multiple satellites in polar orbits lost control for hours. NASA's TDRS-1 recorded those 250 anomalies. The JOE's weather satellites lost communication, causing weather images to be lost. The Space Shuttle Discovery was in orbit. A sensor on one of the tanks supplying hydrogen to a fuel cell showed abnormally high pressure readings on March 13, 1989, and the problem resolved itself only when the storm subsided. This has already happened once, and the record of it is still preserved in the data, in the NOAA archives, in NASA's satellite telemetry records, in the financial and operational reports of Hydro-Quebec, and in the memory of every electrical engineer who has worked in space weather resilience since that date. But 1989 was not the largest event the geological record preserves. It was not even close. In September of 1859, the British solar astronomer Richard Carrington was observing a cluster of sunspots through his private observatory telescope when he witnessed something no one had ever documented before. A sudden, intensely brilliant burst of white light erupting from the solar surface. He recorded it at 11:18 in the morning on September 1st. Within 8 minutes, electromagnetic radiation from the largest solar flare in 5 centuries reached Earth's ionosphere. within 17 hours, an astonishingly short transit time indicating a CME traveling at approximately 2,300 kilometers per second. A coronal mass ejection struck Earth's magnetic field with a force estimated to be roughly twice the strength of the 1989 event. There was no power grid in 1859 to collapse. But there was the global telegraph network, and the Carrington event demonstrated precisely what an extreme geomagnetic storm can do to any conductive infrastructure connected across long distances. Telegraph systems across Europe and North America failed. Operators reported that their equipment was producing sparks even when disconnected from their batteries. Some telegraph offices caught fire as the induced electrical currents exceeded what the wiring could carry. The aurora borealis, the northern lights produced by the solar particles driving into Earth's atmosphere, was so intense that people in the northeastern United States could read newspaper text by its light in the middle of the night. People in the Caribbean reported seeing the aurora for the first time in their lives. If the Carrington event occurred today, and scientists who study ice cores from Greenland and Antarctica, where the chemical signatures of historical solar particle events are preserved in annual layers of accumulated ice, confirm that Carrington-scale events have occurred multiple times in the last 10,000 years. The estimated total United States population at risk of extended power outage ranges between 20 and 40 million people. Duration estimates, developed by NOAA and published research, range from 16 days to 1 to 2 years for full grid restoration, depending on the scope of transformer damage. This is not science fiction. This is risk assessment conducted by the same agencies that issue the 70% radio blackout probability that NOAA's Space Weather Prediction Center is maintaining. Today, for the environment produced by active regions, AR4420 and AR4425. The question is not whether. The question is when. Now consider the connected systems. Because a solar event of sufficient scale does not operate on a single front, it operates simultaneously across every dimension of the technological infrastructure that the modern world depends upon. And the interconnection of those dimensions is what transforms a large solar flare from a regional problem into a civilizational one. Begin with GPS. The Global Positioning System and its international equivalents, the Russian GLONASS, the European Galileo, the Chinese Beidou systems, depends on radio signals transmitted from satellites in medium Earth orbit, approximately 20,000 kilometers altitude, to receivers on the surface. Those signals must pass through the ionosphere. When the ionosphere is disturbed by solar activity, the signals are delayed, refracted, scattered, and the position fixes that aviation, maritime navigation, precision agriculture, autonomous vehicle systems, emergency dispatch, financial market timing systems, and military operations all depend upon become unreliable or fail entirely. In the 2003 Halloween storms, another documented historical event 2 years after the solar maximum of solar cycle 23, GPS position errors during the peak storm period reached tens of meters or more in affected regions. Aviation precision approach systems, which require centimeter-level accuracy to guide aircraft through low visibility to safe landing, went off specification. Airlines rerouted transpolar flights to avoid the highest latitudes where HF radio blackout was complete. And here is where the second connected system enters. Ocean temperature and its relationship to solar activity. The sun's output, including its ultraviolet radiation, influences the temperature of the upper ocean through direct heating and through its interaction with atmospheric chemistry. During periods of elevated solar activity, stratospheric ozone absorption of ultraviolet radiation changes, altering large-scale atmospheric circulation patterns. The ocean is not an isolated tub. It is a dynamic heat reservoir coupled to the atmosphere, and what the atmosphere does determines what the ocean surface does. Sea surface temperature anomalies, the persistent elevated temperature patterns in specific ocean basins that produce conditions favorable for extreme weather systems, are not driven by the sun alone, but the sun is a variable that does not operate independently of the climate system. Researchers at institutions including the Laboratoire de Météorologie Dynamique in Paris and the National Center for Atmospheric Research in Boulder, Colorado, have published peer-reviewed analyses examining correlations between solar cycle phase and regional climate variability, particularly in the North Atlantic and Pacific basins. These connections are not fully resolved. The science is honest about its uncertainties, but the principle is well established. Earth is a single interconnected system, and what moves in the sun sends its signal into the atmosphere, into the ocean, into the ionosphere, into the circuits of satellites, and into the power lines carrying electricity to cities that have no backup plan for the day those lines go down. Think for a moment about the people of northern Scandinavia, of Tromsø, Norway, a city of approximately 77,000 people situated well inside the auroral oval at nearly 70 degrees north latitude, a place where space weather is not an abstract concern but a lived environmental reality. The people of Tromsø depend on GPS navigation during the long polar winters when roads are covered and visibility is reduced. They depend on high-frequency radio for coordination across the vast, sparsely connected Norwegian Arctic. They experience radio blackouts not as theoretical events, but as operational problems, with immediate consequences for shipping, fishing, emergency services, and logistics. When NOAA registers a 70% probability of R1 to R2 blackout conditions and a 25% probability of R3 or greater events driven by a sunspot group carrying a beta-gamma-delta magnetic configuration, the people of Tromsø are not among those reading about it on a news website with mild curiosity. They are the people for whom that probability forecast has operational meaning. The ones checking their backup systems, coordinating with Coast Guard and emergency services, filing alternate communication plans. The question those people would ask, if they had access to the full data visible to the professional space weather community right now, is not whether this particular active region will produce an R3 event. That question is unanswerable with current technology. Solar flare prediction remains, in the words of researchers at the Surrey Space Center at the University of Surrey, fundamentally limited. Professor Keith Ryden, who leads the Space Environment and Protection Research Team at Surrey, stated directly in March 2026, with the Artemis II mission preparations underway, that the tools needed to predict what an active region will do simply do not yet exist. The monitoring is in place. Detection is possible. But prediction is not. The question those people in Tromsø would ask is a simpler and more urgent one. Are we ready if it happens today? And the honest answer, based on the data, is that readiness is incomplete. Progress has been made. After the 1989 Quebec blackout, Hydro-Quebec spent hundreds of millions of dollars redesigning its transmission system to be less vulnerable to geomagnetically induced currents. After 2013, the United States Federal Energy Regulatory Commission ordered the North American Electric Reliability Corporation to develop standards requiring power grids to implement at least partial protection against solar storm impacts. NOAA now operates the DS-Cover satellite, the Deep Space Climate Observatory, at the L1 Lagrange point approximately 1 million miles from Earth, where it monitors the solar wind in real time, providing approximately 15 to 60 minutes of warning before a CME impact. On January 23, 2026, NOAA's space weather follow-on Lagrange 1 Observatory completed its final orbital insertion maneuver, taking its position at the same L1 vantage point to enhance monitoring capability. NASA launched the Interstellar Mapping and Acceleration Probe, IMAP, on September 24, 2025, and as of early 2026, it was operating from L1, adding new data on solar particle behavior and the structure of the solar wind. The monitoring infrastructure is better than it has ever been, and yet 15 to 60 minutes of warning before a CME impact is not enough time to safely power down a continental power grid. It is not enough time to safely deorbit or reposition satellites. It is enough time to know that what is coming is coming. It is not enough time to stop it. The thermosphere, the uppermost layer of Earth's atmosphere where low-orbit satellites travel, is itself a record of solar activity. As of May 2, 2026, the Thermosphere Climate Index measured by NOAA stands at 16, 92 times 10 to the power of 10 watts. Compare that to the maximum recorded value in October 1957 of 49, 4 times 10 to the power of 10 watts, during the most intense solar cycle of the instrumental record, and the current value looks moderate. But moderate in thermospheric energy does not mean safe for satellites. It means that the current baseline drag on low-orbit spacecraft is elevated relative to solar minimum conditions. When a major CME strikes and drives the thermosphere into a storm state, that drag increases sharply, and satellites whose operators have not pre-computed contingency orbital adjustments can lose altitude faster than their onboard propulsion can compensate. The solar cycle that governs all of this, solar cycle 25, peaked, according to the best current analysis from NASA and NOAA, in approximately October 2024. The Sun is now in the declining phase of this cycle. There is a temptation, when a solar cycle has passed its maximum, to assume that the danger diminishes proportionally. The historical record instructs otherwise, and it does so with specific examples that leave no room for comfortable assumption. Solar cycle 23 peaked in 2001. The X-28 class flare, the most powerful solar flare in recorded observational history, so intense that it overwhelmed the X-ray detectors on NOAA's GOES satellites and had to be estimated from partial data by the European Space Agency, occurred not at the peak of that cycle, but in November 2003, 2 years past maximum. The Halloween storms of 2003 that produced back-to-back G5, extreme geomagnetic storms, driving auroras to the skies above Texas and Florida and Spain, occurred in the declining phase of solar cycle 23, the most powerful flares of solar cycle 24, an X-13, 3, and an X-11. 88 occurred in September 2017, more than 3 years after that cycle's 2014 peak. The declining phase of a solar cycle is not the safe phase. It is a phase in which the most dangerous individual events sometimes occur, precisely because the magnetic field complexity on the sun's surface continues to evolve in unpredictable ways, even as the overall sunspot count falls. AR4420, identified as still carrying a beta-gamma-delta magnetic configuration as recently as April 29, 2026, is exactly the kind of active region that delivers this lesson in real time. This is not a region that is weakening on a predictable schedule. It is a region that forecasters at EarthSky described in sourced observations compiled from images obtained by amateur solar photographer Victor Rogas on April 29th, as still harboring the energy for X-class flares. The system is not inactive, it is accumulating. What the official data actually shows, assembled from NOAA's Space Weather Prediction Center alerts, from NASA's Solar Dynamics Observatory, from the Space Weather Live Monitoring Network, from the UK Met Office Space Weather Forecast issued around May 1st, 2026, and from the 7-centimeter radio flux reading of 143 solar flux units maintained through the end of April, is a sun operating at elevated active levels, producing flares from two complex sunspot regions that have dominated the solar disk for weeks, generating ongoing R1 radio blackout conditions with a formally documented 70% probability of R1 to R2 escalation and a 25% probability of R3 or greater events, while the planet below continues the business of modern life in a state of dependency on the electromagnetic infrastructure that solar activity is capable of disrupting. Aviation, shipping, emergency coordination, GPS navigation, satellite telecommunications, power grids serving populations measured in the hundreds of millions, all of it resting on the assumption, not the guarantee, but the assumption that the sun will not, in the next hours or days, produce the kind of event that its active regions currently have the magnetic energy to generate. Scientists choose their language carefully here, and that careful language is itself the warning. When a NOAA forecaster writes that AR4420 retained its beta-gamma-delta magnetic complexity, and that a 25% probability of R3 or greater radio blackout events exists through the coming days, that sentence is not a sentence written for dramatic effect. It is a sentence written by a professional who has read the magnetic field maps, who has reviewed the flare history of similar active regions, and who understands that 1 in 4 is not a small probability when the consequence is hours-long HF radio blackout across the sunlit hemisphere of a technologically dependent planet. 1 in 4. That is the odds that in any given game of Russian roulette played with 4 chambers, but with stakes measured not in individual lives, but in the communication and navigation infrastructure of an interconnected global civilization, the chamber fires. The Carrington event of 1859 left its signature not only in historical records and in the accounts of telegraph operators who felt electrical shocks through their equipment, but in the ice. Ice cores drilled from the Greenland ice sheet and from Antarctica contain annual layers of accumulated snowfall going back hundreds of thousands of years. Within those layers, the chemical signatures of major solar particle events are preserved as elevated concentrations of nitrate, produced when high-energy solar protons interact with Earth's atmosphere and drive nitrogen into its oxidized form. Analysis of these ice cores reveals that Carrington-scale events producing the level of solar particle bombardment that occurred in 1859, are not once-in-a-millennium anomalies. They appear in the record with a frequency that, while irregular, is measured in centuries rather than millennia. They have happened before the telegraph. They have happened before electricity. They have happened before the satellite. And they will happen again with complete indifference to the timing of financial quarters, to the orbital schedules of telecommunications constellations, to the flight plans of transoceanic aviation, and to the question of whether the power transformers serving a city of millions have been hardened against geomagnetically induced currents. The instruments watching the sun on May 3rd, 2026 are the best instruments humanity has ever deployed. NOAA's GOES-16 satellite, now the primary and exclusive geostationary source for space weather data after GOES-14 and GOES-15 were placed into storage mode, monitors the sun's X-ray output in real time, and triggers alerts automatically when the threshold for M-class and X-class events is crossed. The SWFO L1 observatory stationed at the L1 Lagrange point as of January 23, 2026, provides upstream solar wind data that gives forecasters their 15 to 60-minute CME impact warning. NASA's IMAP observatory supplements this with data on the structure of the heliospheric environment through which solar storms travel. The monitoring has never been better, and what that monitoring shows, as of the date of this script, is a sun that has not produced a spotless day since early 2026. A sun whose 7-centimeter radio flux remains at 143 solar flux units, a sun whose active regions carry the most dangerous magnetic classifications, and a sun whose behavior in the days immediately ahead carries a formally quantified 70% probability of radio disruption across the sunlit side of Earth. Minutes are not hours, and in this context, the distinction between the 15-minute warning NOAA's upstream monitors can provide before a fast CME impact, and the hours that would be needed to safely respond to one is not a gap that can be closed with currently deployed technology. That gap is the distance between knowing and being prepared, between the alert and the action, between the instrument reading and the infrastructure response. And in that gap lives every pilot flying a transoceanic route on high-frequency radio backup, every Coast Guard station coordinating search and rescue across Arctic waters, every power grid operator watching the geomagnetic field indices tick upward and calculating whether to initiate a controlled reduction in grid loading before the induced currents arrive, or to wait and see whether the storm peaks below the threshold that would make that decision necessary. The sun produced the light that made life possible on this planet. It has been burning for approximately 4.6 billion years. It has another 5 billion years remaining in its main sequence lifetime. In the total account of that 10 billion year span, the 78 years since the first artificial satellite reached orbit, the 78 years in which the human species placed its communication, navigation, and power infrastructure in a position where the sun's behavior could threaten it, represent a fraction so small it has no meaningful name. The sun was doing this long before there was anyone to measure it. It was producing X-class flares, coronal mass ejections, geomagnetically induced currents, and radio blackouts on geological timescales, when the only receivers were the magnetic minerals in the rock that would one day become the Canadian Shield, quietly recording the evidence of what had passed, waiting for the instruments that would eventually learn to read them. The rock remembers everything. And what the rock remembers is that this has happened many times before, and will happen many times again, with or without the 70% probability that NOAA has assigned to the next few days, with or without the monitoring satellites watching from L1, with or without the power grid protection standards ordered by federal regulators, with or without the emergency communication protocols, and the backup navigation systems, and the hardened military communication networks. The sun does not negotiate with the infrastructure it threatens, it simply accumulates. And then, when the magnetic fields can no longer hold what they have been building, it releases, at the speed of light, across 93 million miles of interplanetary space, into the ionosphere of a planet that has been orbiting quietly beneath it for 4.5 billion years, and has been calling itself technologically advanced for less than 200 of them.